Hello everyone, I'm Luca Zanolini and I will present you our joint work with Orestis Alpos and Cachin on how to trust strangers. This work will show how it's possible to compose Byzantine Quorum systems under different models of trust. Secure distributed systems rely on trust. Trust assumption specifies the failures that a system can tolerate and determines the condition under which it operates correctly. Trust is defined through a fail-prone system that is a collection of subsets of participants in the system or processes in the system that may fail together and that are tolerated in a given execution. Through this work, we indicate this fail-prone system with this cursive F. Originally, trust assumption has been symmetric. This means that every participant in the system shares the same view of trust and shares the same global fail-prone system. More recently, new models of trust have been studied, and this is the case for the asymmetric model of trust, a generalization of the symmetric model of trust in which every participant in the system is free to choose who to trust and who to trust not, expressing their beliefs in a subjective fail-prone system. The collection of all of these subjective fail-prone systems makes an asymmetric fail-prone system. Because of its characteristic, this model of trust is well suited for blockchain. We were driven, in fact, by the question of how it's possible to compose different blockchains with the same underlying model of trust. In this work, we give an answer to this question by showing how to compose different trust assumptions, and in particular, we show deterministic rules that are able to join together trust assumptions, and in particular, that are able to join together fail-prone systems. We do so in both the symmetric model of trust and in the asymmetric model of trust. Let's start then with the symmetric model of trust. Let's start by defining a Byzantine quorum system. A symmetric Byzantine quorum system is a collection of sets of processes where each of these subsets is called quorum, such that these two properties are satisfied. The properties consistency says that for every two quorums in a quorum system and for every subset inside a fail-prone system, then the intersection between these two quorums is not fully contained in F. Moreover, the availability requires that for every fail-prone set or for every subset inside a fail-prone system, it exists at least a quorum such that the intersection with this F is fully empty. An example is the classic threshold model, in which a quorum is any set of cardinality at least n plus f over 2, where f is the total number of failures in the system. The goal is to find, as I said, composition formulas that are able to join together different fail-prone systems. We do so by showing two systems, but of course our work can be extended to multiple systems. We show how, given two systems, one system with its own global symmetric fail-prone system and another with its own fail-prone system, in which these systems can or cannot have common processes, the goal is to find a composition rule that is able to give a composite fail-prone system with some properties. One of the properties is that from this composite fail-prone system, we're always able to derive a Byzantine quorum system. Moreover, we want that given a fail-prone set, given a set of processes inside this composite fail-prone system, we want this to be derived from the two original fail-prone systems, and we don't want this to arrive from nothing. Again, we want this to be derived from the two original fail-prone systems. We do so by showing three different formulas, each of them with different properties. Let's start by showing this example, and through this example I will show all of our formulas. So let's consider two systems, system P1 and system P2, system P1 with processes from A to E, and system P2 with processes D, E, F, G, and H. Of course, we can see here there are two common processes that are D and E. The fail-prone system for system P1 is given by the processes A or B and C, or D or C and E, while fail-prone system for system P2 is given by D or E or F and G or H, as we can also see in the picture. Our first formula is what is called union composition, which is simply the union of the two different fail-prone systems. The result is given by this underlying formula, by this result, And this is well suited. It's possible to derive a Byzantine quorum system, but there are some pitfalls. For example, taking a subset inside this composite fail-prone system, we can see that, of course, this is derived from either one fail-prone system or in the other, but we cannot see actually a sort of composition between the two. We cannot see actually a composition between the fail-prone sets inside the fail-prone systems. And this is something that we want. We want also to be able to join together, to tolerate also the other in composition with the others. So what we want is to refine this formula, and we do so by presenting our first Cartesian composition formula, and this is given by the pairwise union between the fail-prone sets in the two different fail-prone systems. This, of course, as we can see, leads to many more fail-prone sets inside the composite fail-prone system, but this formula has some pitfalls. In particular, we prove how, given fail-prone system with common processes, it may be the case where it's impossible to derive a Byzantine quorum system. So, starting from this formula, we want to refine a little bit more to obtain the characteristics that we want, the properties that we want. And we saw with our final Cartesian composition formula number 2, and this again given by the pairwise union between fail-prone sets in the different fail-prone systems, but with a property more. And this property says that for every set of common processes, then this set is either contained in both the fail-prone sets that we are going to do the union or in none. It's not possible then to find a common process that is contained in one fail-prone set but not in the other. This would violate properties that we are expecting, and this again wouldn't lead to a Byzantine quorum system. Of course, everything is proved in our technical paper. Here, the composite fail-prone system results in this. As we can see, if we take, for example, one fail-prone set, we can see that this is actually a composition between one and the other, and it doesn't violate any property that we were expecting. And this always leads to a Byzantine quorum system. So this is the formula that we were looking for, and this concludes the part related to the symmetric trust assumption. Let's move now to the asymmetric part. We generalized the definition given before about the asymmetric Byzantine quorum system by defining an asymmetric Byzantine quorum system that is a strict generalization of the previous symmetric definition. An asymmetric Byzantine quorum system for an asymmetric fail-prone system is just an array of collection of sets, and these sets are the quorum systems of every participant. Moreover, we require these two properties that are a generalization of the two previous described properties, and again are consistency and availability. In this model of trust, in this asymmetric model of trust, we don't have anymore the simple characterization that we have in the symmetric case with correct processes and malicious processes. But among correct processes, we have a broader classification, and this broader classification is given by the fact that a correct processes may be able to foresee the actual failures in a given execution or not. More specifically, a correct process PI, a correct participant PI, for which the set of the actual failures in a given execution is not contained in its fail-prone system, is called naive. A correct process PI for which instead is contained in its fail-prone system is called wise. This is important because wise processes can collaborate together by forming what we call a guild. A guild is a set of self-sufficient participants, a set of sufficient processes that can continue to operate in a given execution in the presence of malicious processes. An example, let's consider this asymmetric Byzantine quorum system given by 4 processes, blue, orange, green, and red, and by assuming the red to be the malicious in the execution, we can see that process blue, orange, and green form a guild. Why? Because we can find at least one quorum for each of them in which the process red is not contained. This means that they don't have to listen to the process red to continue to operate. They form a guild, and more specifically, more technically, a guild is a set of processes such that for every process in the guild, it exists at least one quorum fully contained in the guild. In this case, a guild is made by process blue, orange, and green, as I said, and in fact, we can see that for process blue, we can find a quorum that is the quorum made by blue, orange, and green that is fully contained in the guild. We can have, of course, more difficult, more interesting scenarios in which, for example, let's consider this 7 processes case where process red and yellow are malicious. In this case, we may be able to find a guild made by process blue, orange, and green. We can have a naive process that wasn't able to foresee that these 2 processes were malicious, but there can also be cases in which we have wise processes outside the guild. This, of course, requires a bit more technicalities that can be found in our technical paper, but what is important here is to notice, again, what is a guild. A guild is a set of self-sufficient processes that together can continue to operate in a given execution. So, if given an execution and given a guild in this execution, a guild is self-sufficient to continue to operate alone, then the remaining processes in some way can be considered as useless in some way. By this observation, we define what is called a tolerated system. Tolerated system is a collection of all the possible subsets of useless processes in different executions in which a guild can arise. This means that if we take a tolerated set inside this tolerated system, this is made by, again, useless processes that do not influence the guild. For example, in this case, a tolerated set can be made by red, yellow, purple, and black, because the guild in this case is blue, orange, and green. We prove how the tolerated system for an asymmetric fail-prone system is actually a Byzantine Quorum system, and this will be very important later. The goal is again here given 2 or more, but in this case given 2 asymmetric systems with common processes or not. The goal is to find a composition formula that is able to compose this asymmetric fail-prone system, resulting in a composite asymmetric fail-prone system that always leads to an asymmetric Byzantine Quorum system, and for which it's possible to find given a set inside this composite fail-prone system. Again, this is generated by the original asymmetric fail-prone system and doesn't come from anything. This was very important for us to be able to reach a scenario, a formula in which we compose without having to generate new assumptions, but everything is made by compose already existing fail-prone systems. So before showing you the formula, I need to introduce quickly a mechanism that is called purification mechanism. The reason why we need this purification mechanism is the following. Given this asymmetric model of trust, given different asymmetric systems, we may have a lot of different possible combination of beliefs expressed by these asymmetric fail-prone systems. So it may be very difficult to find a scenario in which it's possible after the composition to always find an asymmetric Byzantine Quorum system. For this reason, if two sets of participants, to system or to groups of participants want to work together and join together, in some way we can think about that they need to adapt in some way to the beliefs of the other, respectively. And we do so how? Through this purification procedure. The purification procedure at very high level removes fail-prone sets that are useless in the sense that they do not influence the existence of a guild. Of course, this is explained in much more details with proofs in our technical paper, but this is just the idea of why we need this. We need to purify the fail-prone systems such that we are able to compose them and to always have a Byzantine Quorum system. Anyway, the processes, the fail-prone set we are going to remove from these asymmetric fail-prone systems are anyway useless in the sense that they do not influence the existence of a guild. And we know that a guild is a self-sufficient set of processes, set of participants that can continue to operate. So this is all good. The formula is given through this example, let's consider again two asymmetric systems, the first one given by A, B, C, D, and E, and the other system P2 given by F, G, H, E, I, and J. Here they are disjoint, but we prove in our work that our formula works also in the case of systems with common processes. For example, the fail-prone system from process A is given by C or D or E, and so on and so on. The tolerated system for system P1 is given by the subset A and B, or C or D or E. This means, for example, that if AB fails, then we can have a guild made, for example, by C, D, and E, for example. The tolerated system of the second system instead is given by F or G and J or H or I. We assume that the two asymmetric fail-prone systems are purified. This is essential. So, given this, the formula is the following. I will explain you. So, we know that, as already introduced before, a composite asymmetric fail-prone system, or in general, an asymmetric fail-prone system, is a collection of different subjective fail-prone systems. This means that also the composite asymmetric fail-prone system will be an array, a collection of different fail-prone systems. How we obtain this different fail-prone system? Just by applying at each member of this array the symmetric Cartesian composition rule introduced before, between, for example, in the first position, between the symmetric fail-prone system, the subjective fail-prone system for process 1, with the tolerated system of the other system, and so on and so forth. So, if we want to determine, in this case, for example, the fail-prone system of process H inside this composite fail-prone system, what we need is to apply the symmetric Cartesian composition rule between, for example, the fail-prone system of process H with the tolerated system of the other system. We know that, in fact, that the Cartesian composition formula in the symmetric case works between Byzantine systems. And we showed before how a tolerated system is a Byzantine system, quorum system. So this works perfectly, and this is what exactly we wanted. For example, the subjective fail-prone system of process A inside this composite fail-prone system is given by the formula below. This is what we show how, through this formula, it's always possible to reach an asymmetric Byzantine quorum system. And this is the formula that we wanted and we were looking for. Finally, in our work, we also sketched a protocol on how to initiate the composition between two or more systems. But of course, I remind you to our technical paper for every proof and every other details. And that concludes my presentation, and thank you very much.